So here we have our audio file, the original audio file which we downloaded from internet, the white Gaussian noise, and this is the recorded file. So this we have played it from our laptop and recorded it on our phone in the room. So both we are giving it in this LMS block. So our y of n is going as input and the x of n is our desired thing, and this is our room inverse filter. So let's come over here. So this is our case, x of n room, y of n. This is the recorded, this is the original one. So we already have this thing, y of n, and we are estimating FIR filter. So we have passed y of n as input to FIR filter such that we get x of n. So this thing, the output error gives the error, this is the weight, and this thing plays the approximate x of n. The error and the weights are being transferred to the workspace here. So this was the 50-second audio. So this is our original x of n, and weights we have taken from our workspace. The buffer block takes the audio samples in the rate 32, and those are multiplied to give us this audio. So what we are doing here is that we are multiplying x of n with this weights of this FI room inverse and getting x1 of n. Now as this plays, we'll record the video from the room so that we get x hat of n. We'll trim both videos to 40 seconds, and then we'll compare both, like we'll take this thing and the original x of n and like calculate the PSQ value as well as x of n and y of n. So here we have the PSQ code from the GitHub repository as recommended. This is our PSQ function calling. So here we give the two files of which we are the reference file as well as the file of which we the PSQ we have to calculate. First let's calculate the PSQ of x of n and the recorded one, which is the y of n. So here it is calculating the PSQ, and as you can see the score is 1.153. Now we have recorded the output from the laptop after the room inverse, and that we have stored it as process.wave. Now when we compare it with process.wave, we must get the value close to 4.5 because it is approximately equal to the x hat, it is approximately equal to the audio dot wave. So here it is calculating and we get 4.505, which is a good result. So here in the question, as you can see, we have solved most of the part. The only part which remains is we have to measure the impulse response between phone A and phone B. So the part which we previously explained was a part of the room equalization problem. Here we have to measure the impulse response of the room, which is a system identification problem. So here I have written a code for the system identification problem. Audio.wave is our input x of n, recorded.wave is our output y of n, right? And here we are writing the code for our system identification. We have initialized h here, mu is the LMS algorithm, we have kept mu as 0.01. And here we are running our LMS algorithm here. Error is d of n minus y hat of y hat, and this is our update rule. So on running this, we must get h, which would be our h of n. So this would be a 32 cross 1 vector. Yeah, as we can see here, h of n is this 32 cross 1 vector.